Hi everyone, welcome back to yet another Euphoria Academia YouTube video. Today we're going to be doing the Physical Sciences Paper 1, May or June paper that was written in 2023. My name is Ole and I'll be taking you through it. So without waste of time, let us get into it. Right. Today we're going to be doing questions on projectile motion. We're going to be focusing on question 3s. Alright, so we are going to do this question. It starts from 3.1 and it ends in 3.3 and it carries a maximum of 15 marks. So let's get into the meat of the question. Let's understand exactly what's happening here. Alright, so we have a ball that is dropped from rest from the top of a building that's 15.2 meters high, and after the ball A has fallen about 3.2 meters, we have a second ball, ball B, that is projected, that is going to be launched upwards from the ground, and after some time the two balls are actually going to end up in the same place, which is the ground. So they're going to hit the ground at the same time. Crazy. Alright, so we're told to ignore the effects of air resistance, so that means we're dealing with projectile motion. So let's put some animations to understand this question a bit better. So to start off, we have some ball at the top of a building, right? Now this ball is going to be dropped and then it's going to pass 3.2 meters where a second ball is going to be launched, and as the ball is launched they are both going to hit the ground at the same time. Alright, so we're going to start with question 3.1, and question 3.1 is asking us to define the term free fall. Now with every physics paper, you're going to be asked to define something, so it's important to know your definitions. But free fall is basically when the only force acting on an object in motion is gravity. That's free fall. Now question 3.2.1 is asking us to determine the time taken for ball A to strike the ground. So we just have to define what we call or what we will deem as positive in terms of the direction. So I'm going to take downwards as positive. So downwards will be positive, which means that our acceleration due to gravity is also going to be positive. And yeah, we just need to take note of that. So the time taken for the ball to strike the ground. So we know how high the ball is from the ground. So it has to travel a distance of 15.2 meters to the ground. We know that initially its velocity is 0 meters per second, and we also know our gravitational acceleration, which is 9.8, and it points down. Alright, so let us use an equation that's going to help us determine this, and we're looking for the time. Okay, so we can use this equation that says delta y is equal to vi multiplied to delta t plus half a delta t squared. Right, now delta y is 15.2 because essentially we're going from up all the way down, and the down distance is just this 15.2 meters. Our initial velocity is 0, so that term goes to 0, plus half of 9.8 multiplied to delta t squared. Now, doing some algebra, we're going to find that the time taken for the ball to hit the ground is 1.76 seconds. Okay, so now we're going to be doing question 3.2.2, and it is asking to find the magnitude of the velocity with which ball B was projected from the ground. So we need to find the initial velocity of ball B. Right, now we know that after ball A travels a distance of 3.2 meters, ball B is then launched. All right. Okay, cool. So I guess what we have to ask ourselves is, how long does it take for ball A to pass the 3.2 meters? Because remember, these two balls, ball A and ball B, they are going to hit the ground, right? They're going to hit the ground at the same time. So it's important to know the time ball A takes to get to or passes 3.2 meters, because we even have the final time of ball A. So it's going to give us some sort of indication of where ball B is going to be. All right, so let us get that. So still going to use our delta y, it being equal to vi delta t plus half of our acceleration multiplied to delta t squared. Now we're still taking our downwards as positive. Now our delta y, trying to find out how long it takes after ball A goes or hits 3.2 meters. Our initial velocity is still 0, and then that's going to be half of apologies, not 4, but 9.8 meters per second squared multiplied to the square of the time. Now we're going to find that delta t is 0.8 seconds or 81 seconds. That's how long it takes to pass or how long it takes for 3.2 meters for ball A. All right, now at this time we know that ball B is launched. Ball B is launched, right? Okay, cool. Now the motion for ball B is going to be like a parabola. It's going to go up, then reaches its maximum height, then it's going to hit the ground. All right, but this is happening at the same time as ball A is falling. So we know that at this time, at t is equal to 0.81 seconds, that's when ball B is launched, and then at t is equal to 1.76 seconds, ball B is on the ground as well as ball A is on the ground. Okay, but how long is the motion of ball B going to take? Well, that's essentially the difference between these two times. And this is going to give us a time of 0.95 seconds. That's how long. That's how long ball B travels from start to finish. From start to finish. All right. Now, because of ball B's motion like this, we have something called time symmetry. So it's going to take ball B the same time to go up as well as come down. It's going to be the same time. So what we have to do, you can just divide this 0.95 by 2 to get 0.475 seconds. This is the time it will take to go up as well as the time it will take to come down. Alright, so now that we're just looking for the initial velocity, we can just use this formula. Vf is equal to Vi plus our acceleration multiplied by delta t. This Vf is going to be 0 because we're trying to find the time, not the time, sorry. We're trying to find the Vf that we're defining is when ball B is at its maximum height. Right? Okay, so let's just substitute. We're still taking downwards as positive. Vf is 0, and then our Vi. This is going to be negative. We don't know what it is, but it's going to be negative because it's pointing in the upwards direction. And we know our acceleration is 9.8, and our delta t, which is calculated it, this is the time it's going to take to go up. And it's going to take 0.475 seconds, which will give us a Vi of negative 4.66 meters per second. We can just write 4.66 meters per second going up. All right, now for the last question, which is question 3.3. It asks us that on the same set of axes, draw the position as well as the time graphs to show the motions of both ball A and ball B from the instant ball A is dropped until it reaches the ground. Okay. So we're just going to draw. Okay, that is really not straight. That is horrible. Apologies for that. I'll try and do a better job. Not perfect, but it is better. Alright, so I'm just drawing a set of axes. Now I'm still taking downwards as positive. Now on our y-axis, we're going to have position. On our x-axis, we're going to have time. I'm going to measure time in seconds, position in meters, and yeah. Okay, so let's just consider ball A first. Alright, now ball A starts above the ground at it starts above the ground at 15.2 meters, and then it drops down, right? But being above the ground when downwards is positive at a distance of 15.2 meters, well, we're above, up is negative in this case because downwards is positive. So that means at this position, this displacement of negative 15.2, that's where we are. Now it goes, or it is dropped down, and it reaches the ground at a final time of 1.76 seconds. All right, now here comes the kicker, or the question. Are we going to draw a straight line, or is it going to be a different kind of line? Well, it's going to be a different kind of line because for position versus time graph, the gradient is what? Our velocity, right? This is for a position time graph, and then for velocity time graph, the gradient is the acceleration. Okay, so in this case, our gradient is it constant? If we have a constant gradient, we're going to have a straight line. That means the change is constant. But in this case, our velocity will go from like a 0, and then it'll end up to, for argument's sake, 17.2 meters per second. So that means it changes, the gradient changes. So if the gradient changes, we're not going to have a straight line, but we're actually going to have a line. Let me draw this properly. We're going to have like an exponential sort of line, right? So the line is going to curve, and it's also going to be the same for ball B. So that's our ball A. Now what happens to ball B? Ball B starts at 0.81 seconds, and it's projected up, which means it moves in a negative direction because we're taking downwards as positive. So it is projected up, which means it's going negative, reaches a maximum height, stops at that maximum height, which is above the ground, and then it comes back to the ground again. That's more or less how you would draw this position time graph. Alright, since we have a bit of time on our hands, I think we can do yet another projectile motion question, and we're going to take this question from the Physical Sciences paper 1 May-June paper that was written in 2024. So let's see what we have. So for this question, it is also still question 3. It goes from question 3.1 all the way to question 3.4, and it carries a total of 14 marks. So let's get into it. Maybe let's see some animations. All right. So we actually have a hot air balloon that is moving at a constant velocity of 3.4 meters per second. Then when it reaches 15 meters above the ground, a ball is dropped. The ball hits the ground and then bounces on the ground periodically. All right, so let's see what the first question is. So for question 3.1, it is asking us to still define the term free fall. See, as I told you, we're always going to find these definitions. I'm not going to write it down, but because we've already done it in this question and in this video already. Let's just move on to question 3.2. All right, so for question 3.2, we have a graph that looks like so. So we have, let me quickly draw it. That'll be T1, and then T2 going to have something like this, and that'll be T3. All right, this is also a position time graph. It's also measured in meters. The x-axis is the time, and it is measured in seconds. All right, so the question is, was the ball in free fall between T1 and T2 seconds? Or if you look at it this way, it's kind of like what we drew before. So we already know that the positive direction is downwards, all right? Because we start at some distance, in this case is 15. This 15 meters is above the ground, and then the ball goes to the ground and then waits or rolls around, and then at a time T2 the ball is launched upwards. That's why we're going back again into the negative direction, and then it'll reach some maximum height there. All right, now the question is asking, is between T1 and T2, do we have free fall? Well, the short answer is no. And why do we not have free fall? Well, this ball is rolling around, or it's in contact with the ground. So the forces acting on this ball is not only gravity. So let's just call it Fg is not the only one. Alright. There's probably like a normal force to some degree and all that. So for these reasons, it is not in free fall. For the set of questions 3.3, we're asked to use only the equations of motion. So try not to use other equations or other formulae, because you are going to be marked down. But let's start with it. So question 3.3.1, the question is we need to find the value of T1 indicated on the graph. Now, as explained in previously, the downward direction was taken as positive, right? And we are told that the ball is dropped when the hot air balloon is at 15 meters above the ground. All right, so above the ground, that is negative in this Cartesian form. So this T1 is or has the position 0 meters. So we actually move from 15 meters above ground to 0 meters. So essentially, the question is basically asking us how long does it take for the ball to hit the ground when it is released from the hot air balloon. All right, cool. Now we just want to find the time T1. So we know the distance, we know our delta y to be 15 meters, because that's 15 meters to the ground. And we actually know our VI, our initial velocity of the ball, and it is not 0. I should have written this side, but yeah, it's not 0, and the reason why it's not 0 is because this hot air balloon is moving at a constant velocity. Now the ball is inside the hot air balloon, and if it's inside the hot air balloon while it's moving at this constant velocity, the ball will also have this constant velocity. The ball is not going to be resting because it's moving with this thing. All right. So this constant velocity, we're told that it is 3.4 meters per second, right? And it will be down, which will also make it positive. We know our acceleration. Our acceleration is 9.8 meters per second squared, and that is also downwards, which will make it positive. So which equation can we use? We can use delta y is equal to vi multiplied to delta t plus half of our acceleration multiplied to delta t squared. Now let us do some substitutions. This 15 meters is going to be positive because we're moving 15 meters downwards. And then our VI is also going to be positive at 3.4. Trying to find our delta T plus half of 9.8. That's also positive, and that is our delta T. Now, delta T squared, sorry. Now, from maths, if you want to solve this, what you can use is the quadratic equation, where our A will be equal to 4.9, our B will be equal to 3.4, and our C will be equal to minus 15, because this thing needs to be equal to 0. So we have to take this 15 to the right hand side. Alright, and you're just going to substitute it into this formula, where minus b plus or minus the square root of b squared minus 4ac divided by 2a. And once you substitute these values into that equation, take the positive, because you cannot have negative time, really. This thing is not going back in time. And we will find that t will be equal to 1.44 seconds. All right. For question 3.3.2, we are asked to find the height of the hot air balloon. I'm just going to say balloon. When this ball here strikes the ground. When the ball strikes the ground, what will be the height above the ground of this hot air balloon? Now, we already know that the ball is going to take 1.44 seconds to hit the ground. All right, so that's something that we're going to use. But something to also consider is that in the question, after all the information is given, we are told that the hot air balloon still travels at this constant velocity after the ball is released from it, right? This constant velocity of 3.4 meters per second. Now, if we have constant velocity, if the velocity is constant, that means the acceleration has to be 0, right? Because if you understand velocity and acceleration, how they work, in this case, if our y-axis is velocity, and this thing is constant, meaning we have a straight line. I know it doesn't look straight, but in our velocity time graph, we have said previously that our gradient is acceleration. But if this line is a straight line, our gradient is actually it's not changing, right? So we're just going to have a straight line. So if there is no change, that means there is no gradient. That's why our acceleration is 0. Okay, now that that is out of the way, we can just substitute what we have. So we're trying to find the height, right? And downwards is still positive. Delta y is equal to our vi multiplied to our delta t plus half of our acceleration multiplied to delta t squared. Alright, we're trying to find delta y. Our vi, which is in this case the constant velocity because it doesn't change, 3.4 multiplied by 1.44 seconds. This is when, or this is after the ball hits the ground, plus half our acceleration, 0. So that term is just going to be 0. And then you're going to see that 3.4 multiplied by 1.44 is going to give us an amount of 4.896 meters. Now, this is essentially the distance the balloon travels in 1.44 seconds. But the question was to find the height above the ground. So to find the height above the ground, well, this is just simply that 15 meters that we initially had minus this 4.896 meters, and this is going to give us a height of about 10.1 meters. This is the height of the balloon above the ground. Question 3.4, we are told that the ball was in contact with the ground for 0.2 seconds and left the ground with a vertical upward velocity of 7.2 meters per second. Alright, this is after the ground has this is after the ball has hit the ground. So now we're just looking at the ball hitting the ground. So it's on the ground for about 0.2 seconds, and then the ball is projected up with a velocity of 7.2 meters per second, and then it's going to hit the ground, and then it's probably going to go up again. Alright, now this 0.2 seconds is the difference between T1 and T2. T2 is a different time, and then this maximum height is our T3. So the question is, we have to use the equations of motion to calculate the value of T3 as indicated on the graph. Okay, cool. So we know that this ball moves from the ground to a maximum height, and that maximum height is where T3 is marked off. Alright, but that's not T3. I'll tell you why a bit later in the question. Alright, so we have a VI of 7.2 meters per second, and this is up. This is going up. And then we're looking for the max height, because this is where our T3 is marked off. Okay, and then at this maximum height, our VF is 0 meters per second. And in this case, we still have free fall because it just left the ground, and we were told to ignore air friction, and no other forces were mentioned. So that means our acceleration is 9.8 meters per second, and it acts downwards. Okay, so we are still going to take downwards as positive. Alright, and we're going to use the equation VF is equal to VI plus the acceleration multiplied to our delta T. Okay, now our VF, we said this was 0. Our VI is going to be negative because it is pointing up and we're taking downwards as positive, plus our gravitational acceleration at 9.8 meters per second, and we're trying to find our delta T. Now, after some mathematics, we're going to see that delta T is going to be 0.734 seconds. All right. Now, this time that we have is the time the ball took to move from the ground after that 0.2 seconds, to move from the ground to go to its maximum height. That's the time it took. This is essentially what we got. But the total time, which will be our T3, that takes into account from when the ball hits the ground to it staying on the ground as well as it going up. So essentially the ball is dropping and it will take a time of 1.44 seconds to hit the ground. And then what happens next? Well, it's on the ground for 0.2 seconds, and then it is projected up at that velocity, that's 7.2 meters per second. Then it reaches this maximum height, and it reaches the maximum height after 0.73 seconds. So T3 is actually, the way I drew it, it should be clear. T3 is going to be 1.44 seconds plus the 0.2 seconds it's on the ground, plus the 0.73 seconds that it takes to go up and get on its maximum height. And this total time, this T3, is going to be 2.37 seconds. And that's your question.